Here's a tutorial on section 2.5 of the College Algebra textbook, Transformations of Functions. The topics we'll cover are the transformations of the following functions: quadratic functions, square root functions, absolute value functions, and cubic functions. Let's begin with quadratic functions. You must memorize the parent graph y equals x squared. It has a vertex of 0, 0, which shows up in the middle of the chart if you were creating this chart in order to create the graph. Notice that with the vertex in the middle, we simply count backward, -1, -2 for x, and then again forward 1 and 2. Run these values through the parent graph equation and you'll generate the points necessary to create a rough sketch of the graph. But suppose we're given y equals x plus 5 quantity squared. We begin with the parent graph. The plus 5 is telling us we have a horizontal shift of -5. So move the vertex 5 units to the left. You see we have a new vertex, -5, 0. This is what we call graphing by transformations. Now let's add on a -2 at the end of the equation. We'll start as usual with the parent graph and take care of the horizontal shift, -5, but the number outside the parentheses represents a vertical shift, and it is exactly that number, -2. So now we move the vertex down 2 units, and our new vertex is -5, -2. Notice though the ordered pair represents the opposite of the number inside parentheses, but exactly the number outside. Suppose we have a negative sign in front of the parentheses. We begin by reflecting the parent graph over the x-axis. In other words, we turn it upside down. Now take care of the horizontal shift, -5, and then the vertical shift, -2. The vertex is actually exactly the same, the opposite of +5, which is -5, and exactly -2 for our y value of the vertex. Now let's talk about transformations of square root functions. The parent graph is represented by y equals the square root of x. The significant point here is not a vertex, but rather it's simply an endpoint. And the endpoint actually begins the chart. Notice that the values chosen for the x column are actually perfect squares. The square root of 0 is 0. The square root of 1 is 1. Here we chose 4. The square root of 4 is 2. And the square root of 9 is 3. Plotting the points, we see what actually looks like half of a parabola drawn horizontally. Now let's graph y equals the square root of x plus 4. We begin with the parent graph and perform the horizontal shift of -4. And so we have the new endpoint, -4, 0. But suppose we want to graph y equals the square root of x plus 4 minus 3. Begin with the parent graph. Take care of the horizontal shift. Now we have a vertical shift of -3. So move the endpoint down 3 units. Our new endpoint is -4, -3. And if we have a negative leading coefficient, then of course we begin by reflecting the function over the x-axis. Take care of the horizontal shift, then the vertical shift, and our new endpoint is exactly the same as the previous graph, -4, -2. Now we'll talk about the transformation of absolute value functions. Here is the parent graph. It has a vertex just like the parabola, and the vertex is found in the middle of the chart. Plotting these points, the shape is a V shape. Let's graph y equals the absolute value of x minus 3. Begin with the parent graph. Then take care of the horizontal shift, which this time is +3. You realize that of course it's the opposite of the number you are looking at. We see x minus 3, so the horizontal shift is +3. The new vertex is 3, 0. If we add on a 2 at the end of the equation, we simply start out the same with the parent graph, take care of the horizontal shift, and then vertically we move the graph upward 2 units. So our new vertex is 3, 2. And once again, it's the same pattern. The opposite of the number inside absolute value signs, but exactly the number that we see outside for our ordered pair here, 3, 2. Now let's graph one where the we have a negative leading coefficient. So as you know, we reflect the parent graph over the x-axis. We turn it upside down. Take care of the horizontal shift, move the vertex 3 units to the right, and then the vertical shift, move the vertex 2 units upward. And of course our vertex is still exactly the same, 3, 2. The only difference is the minus sign causes the graph to turn downward. Now let's talk about our last function, the transformation of a cubic function. Here is the parent graph, y equals x cubed. It doesn't have a vertex. It has something called an inflection point. But yet, it's similar to a vertex in that the inflection point is mentioned in the middle of the chart. And notice from 0, we counted backward, -1, -2, and then from 0 forward, 1 and 2. Simply run these values through the equation and we get the corresponding y values. When we plot them, this is what the parent graph looks like. This point right here at the origin, called the inflection point, indicates where the graph changes from concave down, here's concave down on the left, to concave up to the right of it. Now let's graph y equals parentheses x minus 2 raised to the 3rd power. Begin with the parent graph. Then take care of the horizontal shift, +2. Simply move the inflection point 2 units to the right. Our new inflection point is 2, 0. If we add on a 3, then of course we begin with the parent graph. The horizontal shift is +2 and the vertical shift is +3. We move the inflection point to the right 2 and up 3. And our new inflection point is 2, 3. Now lastly, let's show one that has a negative leading coefficient. I show the points this time because turning this upside down is just a little bit harder to visualize. But here we have negative the parent graph. We reflect it over the x-axis. Now take care of the horizontal shift, +2, and then the vertical shift, +3. So you can see by moving to the right 2 and up 3, we have the new inflection point 2, 3. And this ends our tutorial on section 2.5, Transformation of Functions.